In this paper, we shall show that the integral from 1 to infinity of floor x over x to the power s plus 1 is equal to zeta of s over s. This paper is presented by Pablo Manalastas, retired faculty of Ateneo de Manila University. The Riemann zeta function is defined as the summation from 1 to infinity of 1 over n to the power s, where s is a positive integer. When s equals 1, zeta of 1 is the harmonic series, and so zeta of 1 diverges. For small values of s, say s equals 2, 3, 4, 5, 6, 7, the computation of zeta of s converges, but convergence is slow when double precision is used. There is no problem of convergence for higher values of s. More efficient ways of computing zeta of s have been discovered. These are computation of zeta of 2 as pi squared over 6, which is also called Bassel's constant, and the computation of zeta of 3, or Apéry's constant, computed as this complicated summation involving combination 2k over k. This looks complicated, but it's actually faster converging than if we use the original definition. Our integral of interest, f of s, can be written as an infinite sum of integrals over unit intervals, integral from 1 to 2 plus integral from 2 to 3 plus integral from 3 to 4, and so on. We can write this compactly as summation from 1 to infinity of integral from n to n plus 1 of floor of x over x to the power s plus 1. In the unit interval from n to n plus 1, the value of floor of x is n, so we can replace this floor function by n. The cases of s equals 0, 1, and 2 will be considered later. We shall show now that the sum converges for values of s from 3, 4, 5, etc. For s equal to 3, 4, 5, etc., we can evaluate the integral from n to n plus 1 as follows. This is just x to the power minus s minus 1, and by the integration of a power, this is the integral. Evaluating at the bounds, at the limits, we get this. The first summation we call a of s, and the second summation we call b of s. When for the values of s we are considering, a of s converges to zeta of s minus 1. Actually, a of s converges for these values of s. In b of s, if we replace n plus 1 by k, we get this. And when we distribute the summation sign, we get b1 and b2. b1 converges to zeta of s minus 1 minus 1, and b2 converges to zeta of s minus 1. This is actually zeta of s excluding the first term. That's why we have zeta of s minus 1. So plugging in these two values into b, we get this. B of s is zeta of s minus 1 minus zeta of s. When we substitute the values of a of s and b of s into f of s, we get the desired result. Thus, we have proven that f of s equals zeta of s over s. Now we consider the values of s 0, 1, and 2. F of 0, for f of 0, the denominator is just x, and the integral is log x, which we evaluate from n to n plus 1. We get this series which telescopes into f of 0 equals minus log 2 minus log 3 minus log 4 and so on. And so it's easy to see that f of 0 diverges. When s equals 1, the denominator is x squared, which we integrate as x to the minus 1 over minus 1. And evaluating at the endpoints, this is what we get. And combining this and canceling the n, canceling the n, we get this. Changing the counter from n to k, where k is n plus 1, k starts from 2, so this is zeta of 1 minus 1. Thus, f of 1 diverges also. However, when we go to f of 2, we see that f of 2 actually converges, because this is x cubed, which when we integrate, we get minus 2x squared in the denominator. Evaluating at the endpoints, this is what we get. And then we distribute the n into the two terms, we get this. In the second summation, we replace n plus 1 by k, and this is what we get. So distributing the summation here, we get these two terms, and combining these first two, we see that this is actual, this and this are equal except for the first term, which is 1/2, and subtracting gives 1/2 here. This one is actually zeta of 2 minus the first term, which is 1. Combining the two, we get f of 2 is zeta of 2 over 2. Combining this with the first result, we now conclude that the integral from 1 to infinity of x to the floor x over x to the power s plus 1 is zeta of s over s for values of s 2, 3, 4, etc., which is what we originally wanted to show. Thank you. That's the end of the presentation.